So good morning, everyone. My name is Christian Hennemann. I'm senior scientist at Fraunhofer IWU in Germany, and I have the honor to present the first session as a session chair. The session is called Circular and Lightweight Design in High-Performance Battery Packs. But before we start this session, I want to say that we talk about technology today, about processes, about lots of technical things. I think the most important issue on that project is the family that got together here. Okay? We have a great collaboration team and it worked perfect. So thank you for that. This clapping was for all of you. So first of all, we have Tony Lara. Please come on stage. He will present I would say lots about modularity of batteries. He has a bachelor's degree in mechanical engineering, is a master's degree in material science and product design, 20 years of experience, and I recognize he's not only a material expert, he is also an expert in design of battery packs. So I'm really curious to see what he has to show today. Thank you. Before I forget it, there is no room for question and answers between all the lecturers. So on the end of the session, we will have a question and answer session. And if you have anything to say, just keep it in mind or write it down, and we will have the chance on the end of the session. Thank you.
Okay. Thank you, Christian, for your kindly introduction, and good morning to everybody, and thank you for staying here. Okay. Okay, then I introduce you the main issues of the main innovations of the battery pack of the MARBEL battery. Okay, so this is the MARBEL battery, and the initial idea of the MARBEL battery is that the battery will be modular, lightweight, thermally optimized, and also easy to assemble and disassemble. Okay, in this presentation, I will explain you how we manage the modularity and also the easy to assemble and disassemble, and then my colleagues from MARBEL explain you more information regarding the lightweight and the thermal management system of the battery. So I introduce you the battery, okay, that it's designed during the last 4 years. Okay, in this battery we have the housing, the modules, all the cooling system, the electric bus bars, all the electronic components, and the connectors. Okay, and regarding the modularity, how we manage to perform this battery modular. In this design, we show you the 2 batteries that we design and then we also manufacture. Okay, one battery from 800 volts and another battery from 400 volts. And as you can see, we use the same aluminum profiles for housing, okay, for the lateral housing and for the bottom profiles also, and the turrets. And the only thing that changed in this case is the length of the profiles. Okay, and also some machinings in the front profile. Okay, regarding the modules, we use the same modules, and the only thing that changed is the number of the modules. In case of 800 volts battery, we use 52 modules, and in the case of 400 volts, we use 16 modules. Okay, what about the electronic bus bars, electronic components, and connectors? Also, we use the same bus bars between modules, okay, the same electronic boards, the same type of connectors, and the same DC box. And the only that it's different from one battery to the other, it's the bus bars to junction box, the junction box, and the number of connectors and electronic boards. What else? Regarding the cooling system, also, we use the same cooling distribution and the same top cooling channels, and the only thing that changed from one battery to the other is the top cooling channels length. And finally, regarding the top cover, we use the same aluminum sheet, the same top covers, the stiffeners, and the only thing that changing in this case is also the sheet and profile length and the number of stiffeners profiles. This regarding the modularity of the battery, but also regarding the easy to assemble and disassemble. In this case, regarding the battery pack, we have the housing. In the housing, all the cell cooling is included in the bottom profiles. And in this case, we use a full aluminum case. In this case, aluminum that is 60% provided from a scrap. Okay, then we attach all the modules, that all the modules are screwed in the housing. Then we attach all the electronic bus bars, all the electronic components and the connectors. And in this case, all the joints are bolted. Okay. Finally, we put the cooling system. Okay. As I say, in this case, all the cooling distribution are screwed in the housing, and the top channels are supported by the top plates of the modules. And finally, we put the top cover that it's also screwed to the housing. To disassemble the battery, we can use the same procedure, but in reverse. Okay, regarding the module, here you have the 12 cells that we put in each module with all the cooling fins and the cooling pads, and also the compression pads. Then we put the housing. In this case, also the housing, it's all in aluminum, and all the components are screwed. Regarding the electronic bus bars and the electronic components, okay, we put all screwed, okay, and finally we put the top cooling lid that it's also screwed in the housing, and in this case the top cooling, the top lid, it's the idea is to cool all the bus bars in the module, okay, and then the same for the disassembly process. We can use the same procedure but in reverse. And it's all for my part. It's a quick overview of the battery pack and also the housing, the module of the battery.
Thank you, Tony. Two advantages, you know. You're very quick and we are back on schedule. So, you know, I just was told I'm typical German, you know, that the clock is still running. So he still has a lot of time. Anyway, there will be lots of questions in the end, I'm sure. And as we keep all them, we will show this QR code on the end again. So if you have any issue, any comments, any further questions, just click on this QR code on the end in the Q&A session, and you will be directed to a place where you get all the information you might need. And as I have some time left, thanks to Tony, I want to mention you have seen how the assembling process is actually working. So you're now all experts. Welcome in the MARBEL family. You can see all the components outside in the foyer, and yeah, you will see all the components, how they are disassembled, and there is an assembled model as well. And at lunchtime, we have the chance to see the battery pack that has been produced in the project MARBEL. But we had a bit of a problem. It didn't fit through the glass doors, and we expect a little bit of rain, so we didn't want to leave it outside. And it's in another building, and we have the chance at lunchtime to go over there and have a quick look. Yeah, so thanks to Tony again. The second speaker is Violetta. She's with Orecut as well. And she's in the advanced researcher at the Waste Energy and Environmental Unit. That's a long name for a department. I wouldn't mention the bachelor, as the vita is quite long, but you have done it in Mexico, so that's something worth mentioning, I guess. And a master's degree in natural resource engineering and a PhD in environmental science and technology. And what I didn't know until I got this vita, she's also a professor in Barcelona on the university, and in the master's program in food development and innovation. That surprised me a bit, because for me, Violetta is not only a dear friend of the MARBEL family, she is also our LCA queen. So I'm really curious to hear and see what you have done. And yeah, it's all your turn. Thank you.
So you've seen a little bit of how the battery is right now from some pictures. You'll see it in real time, real life, at lunch probably. But now I'm going to explain a little bit of the process of eco-designing this battery. Part in complementary part with Tony's presentation from before, where we saw like the final result and how these strategies were applied. So I'm gonna start with how we manage this methodology, how we design the eco-design strategies to apply, and the specific actions. But first of all, let's start with some numbers because this is the important part. How we started, how did we get to MARBEL project at the beginning? Well, turns out the environmental impact of the greenhouse gases emissions in Europe are more or less structured like this. And the transport sector and storage is sharing a 16% of the total of the greenhouse gas emission per GDP in Europe. So this is an important number. It sounds like 16 is not really that much, but it's one of the main contributors to greenhouse gas emissions and global warming potential. So it's important. Then this is why MARBEL project and the European Union started with this program, right, to reduce the greenhouse gas emissions. First, we made a commitment with the Paris Agreement where we had to stay below the 1.5 degrees in global warming. And I think we reached it already, but we're still trying to keep it at that point. And for that, there's a plan and a strategy to reach this goal. So in this sense, MARBEL is trying to to contribute to these goals and planning, right? And we did this by following the four circular economy categories, which is the circular support models, the circular design models, the optimal use, and the value recovery as well. With what Tony was saying before, the modular design, improved features of the battery to improve the lifetime and the performance of the battery, to increase the, to make it more long lasting, and also to make it more easy to assembly and disassembly, not only for cost and time improvement, as Eduard was saying at the beginning, but also to improve the end of life possibilities to recover the materials and components, right? So it has to be a battery pack that Eduard and Tony were explaining. It has to be flexible, it has to be versatile, it has to be modular so that we can use the components after the first life of the battery in other uses probably. And for this, well, the main issue with eco design is that we have to prove that it has lower environmental impact. No, that's the word coming from. And for this, we use the life cycle assessment methodology. But this is not enough. So we design in EURECAD, we design and applied a design for circularity or eco design methodology that follows the four, let's say, the PDSA program, which is in this case, the identification of hotspots, strategies to readapt the strategies to the technological procedures to see if it's really feasible, and then a definition of specific actions to apply. But all this was started with first to identify the hotspots. We needed first to calculate the environmental impact. So we did it with life cycle assessment. We found the hotspots, and then through this, we found the specific points where we should focus to make a real impact in reducing the environmental impact or the emissions, right? So this is how I more or less explained the methodology before. It's the 4 steps. So first, based on a benchmark analysis with the application of life cycle assessment and life cycle costing in a prospective manner at the beginning of the proposal of the project, we identified the hotspots so that we could focus on it. Then we established the most properly eco-design strategies to focus on. And then on the step 3, we align these strategies with the possibilities. Are these strategies really possible to be applied in this battery pack or at this level of research? And then after this, we conceptualize the battery pack through some specific actions that were applied or that we tried to apply. Some of them were at the end weren't applicable because of the research level at the moment. So a bit of explanation on this step by step. We define this different sheet for the different life cycle stages. So for the raw material extraction and manufacturing of components, we find the hotspots. We focus on the main issues. We calculate the impact. And then for the other life cycle stages, we do the same thing. So we do it we define for MARBEL project 4 different life cycle stages, which is the first one, raw material extraction, the use stage of the vehicle, the second life of the battery applied to another use, which in the case of MARBEL was a scooter, and then the end of life of all the components and materials. And we did this kind of info sheets for each of the life cycle stages, including all the challenges that we were possibly going to face when we apply the strategies. Then we define the strategies also with a set of info sheets, one for each of the strategies. I think we had more than 14 strategies at the beginning, or maybe, yeah. And then we started to cut out the ones that weren't applicable. But at the beginning, there were many, and we studied them in detail, knowing where is this strategy going to have an impact. Is this going to reduce the impact at raw material extraction and manufacturing, or maybe in the use stage? So we cannot see the reduction in the first life of the production of the battery pack, but maybe during the use stage, which is a long time, then we'll see the reduction of environmental impact. So we studied this, including the cost, benefits, or challenges, and the innovative challenges as well. After this repository of strategies, we did an evaluation with the consortium to see if these were actually applicable or viable, feasible in economic way, in technical procedure way. And after this, when we were all familiarized with all these eco-design strategies, we went to the, well, these are the 10 eco-design strategies that ended up as viable or possible. I'm not going to go into detail because then Christian is going to come and tell me something about the time. So, but then we'll go to a few of the actions. And then after the strategies, we conceptualize the specific actions for MARBEL battery. And we came up with 14 specific actions, including, I put ones in big letters so you can read it, and then I'll explain them, but it's using recycled and recyclable materials, reduction of copper in electronic components, it's designed for reuse, dismantling, recycling, a reduce of quantities of soldering or glued parts, introduce weldless connection to cells to support disassembly, and enhance BMS, design a BMS with multi-purpose, anyways. So we came up with these 14 different actions, and this is how we're aiming to reduce the environmental impact. So we did a calculation at the beginning of the proposal of the project, and now we have a new calculation on the MARBEL battery, where all the impacts were reduced in the different life cycle stages. After having this result, we evaluate the actions that were applied and how these are helping reduce the impact of the battery pack. So we created this info sheets again for the specific actions, but now considering the results of the project. So for action 1, it was using recycled and recyclable materials, and mainly the 60% of recycled aluminum that Tony was commenting before for the housing. The challenges that were explained by the different partners of the project is that sometimes it's very difficult to find the amount of the specific alloy that you need for the production, and especially in low batches. If you're not producing in mass, this is difficult to find. So in some cases, this was not possible to apply the recycled content of the materials, but in the housing profile, it was available. Another factor here, a challenge, is that the cost varies too much between materials and times, so it's not easy to forecast this benefit on the cost. The implication of the recycled and recyclable content are mainly in the raw material extraction and manufacturing, and at the end of life. After applying this to the MARBEL project and calculating the benefits of it, we have a reduction of environmental impact during the housing aluminum profiles, that we have a 60% recycled content. So the reduction on carbon footprint would be 777 kilograms of CO2 that were saved only for the housing profiles. Then from the thermal management system was around 100 kilograms of CO2 saved. And the junction box wasn't possible to apply it there because of this mass production problem. But the reduction could be around 11 kilograms of CO2. Then for the plates and handles, it could be again 97 kilograms of CO2 saved. And we don't have the results yet for the end of life of the recyclable amount of aluminum at the end, but it'll be more benefits for MARBEL battery pack. I think the conclusions were already implicit in my explanation, so I'm going to skip them. And then we have the action 7, just as an example, because I said we have 14 and we evaluated by one by one. So this one was to define and include a protocol for the disassembly operations for safety conditions. We have again the description, the challenges. The challenges explained by the consortium was that mainly, well, you have to train the people to do this with a procedure. You have to establish the standard criteria for different similar products as well. And the implications of this are mainly on the second life and the end of life of the battery, because of course this in the case of the MARBEL battery pack, it allows us to even consider a second life of the battery, because otherwise this could be just shredded altogether. Since we have a protocol and it's easy to disassemble, then we can recover some components and give them another life. And the reduction is in around 15 to 30% of the environmental impact in total in the life cycle of the battery. Well, that would be the main issues in the action application during MARBEL. And then the conclusions, well, we really enjoyed working with the consortium because this gives us a lot of feedback, and it was really like a growing process within MARBEL project. We identified the main concerns of this kind of batteries. It was a collaborative approach, resulting in these 10 strategies and 14 specific actions that I explained before. And it allows us to reduce the environmental impact, as Eduard was saying, was the goal of MARBEL, in more than 40% in all impact categories. So I hope you enjoy seeing the results of all this work.
Thank you, Violetta. It's the first time that I see a professor who is in time. Thank you. So the next one, probably the youngest of this group, Elias Atunsari from Asash. I have a very strong connection to Asash as we have a big project together. So I feel already at home in Istanbul. And I was a bit surprised when I saw his Vita, and it's written Senior R&D Specialist. Look at him. Does he look like a senior? Elias is a PhD candidate in metallurgical and material engineering in Istanbul. And his research primarily focuses on the application in automotive and railway industry. I would say today he is the first aluminum specialist who is talking. And yeah, I'm looking forward to your talk. Thanks.
Yeah, thank you, Chris. I'll do my best. So yeah, today it's my pleasure. It's my pleasure to representing Asash and presenting our MARBEL solutions to you. Obviously, we are the producer of the larger scale, industrial scale of the housing profiles. That's why I'm mainly focusing on the machining, extrusion, and welding of the housing profiles. But first, I would like to talk about Asash briefly, and then it will be more makes sense what we've done during the project. So Asash is founded in 1990, and it has now 5 big production facilities. But I would like to focus on now the aluminum profile production. We have really integrated aluminum production extrusion facility, which means that we're starting with alloying and cast the billets in-house. And also we are able to cast from 1,000, 2,000, which contains copper, 6,000 silicon and magnesium, 7,000 zinc, and also like above the Euro norm, 9,000 series alloys during the casting. And the die production, extrusion needs the die, and it is heart of the extrusion process. We are also able to produce the die in-house. And for the extrusion, we have now 8 extrusion presses, and it will be 10 line during at the end of the year. And the biggest one is 62 meganewton and is now the biggest one in the Turkey as well. And with that, we are able to produce 600 millimeters wide profiles for it. And additional, the added value coming from surface treatment and also mechanical treatment, we are able to make anodizing, electrostatic powder coating, and on the mechanical treatment side, machining, bending, punching, and also joining, also welding of the profiles. So yeah, those are the investments here. Why I'm telling you this? Because we produced MARBEL profiles in our brand new 45 meganewton press, which is directly dedicated to automotive industry. And at the end of the year, we will be having 150 meganewton press, and it will be the biggest for Europe. And also in our flat roll product, we will be having new cold rolling mill investments. For the R&D, so especially we focused on this project, MARBEL project. We are able to make the new computer-aided engineerings and also imaging laboratories. We made it to the profiles that produced for the MARBEL project, and with scanning electron microscope, plugins with EDS and EBSD, and of course mechanical testing, including tensile testing, bending, surface roughness. It is also important for the extrusion itself. And for the alloying, chemical analysis, like for optical emission spectroscopy we do have, we also implemented all these tests during the stage. So now you can see the battery housing production route. It starts with alloying, aluminum primary ingots, and also above 60% scrap, and alloying elements and additional titanium boride, etc. And also melt treatment has been carried out. And the next step is direct chill casting. With direct chill casting, we are producing the billets, which is the main input material of the extrusion process. And of course, it is followed by homogenization, because in extrusion, theoretically, you can produce kilometers of profiles. And it's really important to have the homogeneous microstructure, homogeneous mechanical properties. This is an inevitable stage as well. And for the heat treatment, we used a 6063 alloy for MARBEL. Of course, in the Euro norm, it is really wide range, and we need to focus on the simple elements like silicon, magnesium, chromite and also other stuffs. So and since 6000 series alloys can be strengthened by precipitation hardening, it's important to get them to T6 condition. Also, we also worked on it. And of course, CNC machining of the profiles, cutting in the suitable lengths for the welding, and also applying the welding, MIG-TIG welding for the battery housing. And of course, after welding, we applied the mechanical treatment as well. And we will be able to see, at least for the on-site attendees, in the prototype of the battery housing. And of course, test and analysis in every step. Tensile testing, hardness testing, and optical emission spectroscopy chemical analysis. We have conducted all of these tests. So left-hand side, you can see during the marble production, it is extrusion press, high breaks, and it's give added value to the eco design because it's high breaks and it works in high efficiency, and also we produce extrusion process itself is really good for mass production. So we're able to produce a lot of profiles to make more testing and to prevent any problem during the welding or other stuff during the prototyping. We produced a lot profiles with it, and also we measured the profiles dimensional changes with Romy dot analyzers. So yeah, Q-form simulation. It is really important for the extrusion because if you produce a die, then you will make you need to make a lot of trials to get the profiles in a good shape, in a good dimension, in real time. That's why we are using Q-form simulation, and we applied Q-form simulation to marble profiles as well. With Q-form, we are investigating the material flow, material heats, because heat is really important on the profiles, since 6000 series alloys can overwhelm with overaging process, and we are losing the mechanical strength. This is why to make the Q-form analysis, investigate the material flow in it, and you can see the results of the material flow and also heats of the material coming out. So yeah, there should be a video. I don't know, maybe we. And yeah, machining and after extrusion and also after welding, you can see the after welding mechanical treatment. We applied mechanical treatment to make the right assembly, and also we worked on not only battery housing, top cover, and cooling channel machining. You can see this is the top cover. It is not 6063 alloy, but the cooling channels inside of it, they are from 6063 alloy, and we produced it, machined it, welded. This is also like the other things we've done during the machining. And yeah, welding, it's really hard since the project is prototyping, not is in serial scale. We have tolerances coming from extrusion, tolerances coming from machining, and also welding. So we need to stick in the tolerances to be able to make the testing, to be able to assembly and disassembly of all the modules in it. And left-hand side, you can see we are welding the bottom profiles, and also we tried to make welding to the lateral profiles. We worked closely with EuroCAD and also Syntef for it, especially for welding. Syntef, they worked on in a lab scale, and we implemented in industrial scale what they've done during this work studies. And of course, during the testing, we investigated the microstructure of the welds, industrial welds. So you can see the heat affected zone, weld zone, and also bulk material. And also we implemented and conducted the tensile testing. Of course, it's inevitable. You're going to lose your strength. You lose your hardness in the heat affected zone, but they are within the standard. So it's all good for the standard side. So yeah, Daniele, I don't know, he's here. I proactively prepared a slide for you. What's next? So we will be focusing on advanced welding techniques, and also we will be increase the post-consumer scrap in circular design methodology. And now, yeah, we are now carrying the battery, but how we are going to manage with the crash performance. And also we would like to focus on in the next project, maybe crash performance of the battery housing of it. And of course, EV battery production and advanced production techniques such as 3D printing and roll foam, etc. Of course, if there is an aluminum, there are steels, coppers, and composites, and also we would like to focus on different material and multi-material solutions. So yeah, I don't know if it's quick. I couldn't follow it, but I hope it's enough. Chris,
It's never enough.
Okay, because I had 10 minutes. So
yeah, you have 1 minute left. So
yeah, okay.
you're speeding.
Thank you for your listening.
Thanks for your talk. As I said already, I have a strong connection to Asash, and to see all the developments in aluminum makes my heart jump. And I said in the introduction from Elias that he's the first aluminum expert we're gonna have a presentation from. Now the second aluminum expert is coming, Sylvia Cruz, part of the Eureka team as well, researcher at the metallic and ceramic material unit. And she has a PhD in material science with more than 13 years of experience, and is busy in a field that I am working as well. So in the development of aluminum alloys, especially based on recycling material. So I'm looking forward to your talk. Thanks.
Now, maybe. Thanks for your introduction, and good morning, everyone. Thanks to be here. Okay, I'm going to explain you the lab scale than before Elias explained you. Okay, I'm going to start with this graph that I'm sure that more than one people here in this room know it. Is the graphic that represents the aluminum in the automotive car, the use of aluminum in the automotive car. Behind this graph, we found the motivation to increase the scrap for aluminum alloys in high performance. But before Nelo tell us that aluminum is included, and bauxite too is included in the critical raw materials. And for this reason, we need to increase the scrap content, the aluminum recycled, and focus in this topic. In Eureka, in our line, we have in this the first part is research high performance aluminum alloy produced with a high scrap ratio, but we need to know what happened with the alloying elements and what happened with the impurities. For the reason, we analyze the properties and their effects in the manufacturing processes, in this case in extrusion process, but we evaluate the impurities. What happened if we increase the impurities? What happened with the mechanical properties, with the microstructure? And I'm going to show you the results that we obtained in the MARBEL project. Our scope was in increase the scrap content more than 50% in extrusion alloys. As Elias told before, we used 60,063 aluminum alloy, and we included 20, 40, 60, 80 until 100% of a scrap. And we use this very little compared with the Elias results, are very little billets that we obtained too. This tooling was designed with the help of Asash, and we designed this special extrusion device. And I'm going to stop a little bit in this part because it was thanks to the MARBEL that we have this tooling. Okay. We don't have in Eureka, we don't have a space to have a very extrusion plant, but we have a very good team, and it was a very hard work team because we have this load press, and our limitation was the force. In this case, only we have 100 tons. For this reason, we designed this special device, and this special device has two parts. One of them is this cam unit that transforms the vertical force into extrusion, horizontal extrusion load. And in this part, we have all the extrusion system with hidden elements, container, stem, and the extrusion die. With this special tooling, we are able to produce profiles, aluminum profiles, and evaluate. The most important for us is the extrudability, because we need to know what happened if we increase the scrap, what happened if we increase, for example, iron, because we found these elements in the scrap, and we evaluate the extrudability with this special device. Okay, I'm not going to go deep this graph, only I'm going to show you that we evaluate, as I told you before, the elements that we found in this case when we increase the scrap, and only to show you that we evaluate, in this case with tensile test, we evaluate the mechanical properties. In this case, our focus was increased more than 50%. Here we found that in the case of 20 and 60% of scrap, the behavior is similar. For this reason, we translate this knowledge to assess to produce the profiles in industrial scale. Now I'm going to say you that MARBEL for us let us the opportunity to start with the knowledge about the use of a scrap, but we continue in our line to increase not only the scrap, but we increase our knowledge, and until now that we have the Free for Leap project, this other European project, that we increase in this case all the scrap in this project. We are able to close the loop because we use battery packs. Of course, the part that extrusion aluminum parts, and we obtain again a profile to use in a new battery. MARBEL, as I told you before, was our first step to increase the scrap content, until this case that we are able to close the loop and increase our knowledge about what happened with the mechanical properties, what happened with the microstructure when we increase the scrap, because everyone talk about the increased scrap, but it's not easy because we found a lot of impurities in the scrap. All of the results, of course, depends on the quality of the scrap and how is this scrap is separate. Okay, and that's all. Thanks for your attention.
Thank you, Silvia. That's working perfectly. Again, I got some minutes left over, so I'm prepared for many questions in the end. Yeah, the next one in the team is Magnus. So he is coming from Sintef and is senior business developer in the department materials and nanotechnology. He has a PhD in modeling and forming and quenching of ultra high strength steel components for vehicle structures. So he's not only busy in steel, as I just said, also busy in aluminum, and we have seen already some developments happening during the last sessions. Yeah, he is responsible for the welding, and so I would say the expert on that. So all the questions you remember, just put them online and we will answer them later on.
Thank you very much. Thank you. All right, we'll try to maneuver this one. I will talk a little bit about the welding and the implications for lightweight design. My title is Welding of Extruded Aluminium, Challenges and Some Mitigation Measures. So the objectives of MARBEL, as you all know, is a lightweight design using the extruded aluminium for the battery pack. We understand that. And the challenge here is to design the welded joint and the welding process for optimized strength. If we consider aluminium, as I say aluminium, but some in Americans say aluminum. But anyway, we all know that if, or not all, but if you weld something with steel, which is the otherwise required material in most car structures and components, it is not very difficult to create a weld and surrounding area that is stronger than the base material, the unaffected zone. So you use a weld material and the surrounding is stronger. So if you have a deformation in operation and use, the deformation is distributed in the unaffected materials. So you doesn't have to consider the weld as a weak zone. In aluminium, in opposite, we have the different problems. In this aluminium, what we use here, which is a precipitated hardened alloy, the weld, it actually destroys the property of the material. So according to current standards, you have to have double the material you would have had needed otherwise. So you had to add double the mass. Aluminium is approximately 1/3 of the density of steel, but a little bit softer. But in this case, you will lose all the benefits of using aluminium if you don't do anything about it. So what is the reason for this? In this picture here, we see that in the we have a laser here. Yeah, there. Sorry. So after welding, this is welds. The heat from the welds is actually then destroying, or in this case, dissolving the small particles, what we call precipitates, that is providing the strength of the aluminium. And further away, they are growing and becoming large, and they also doesn't provide any strength benefits. Further away, it's a non-affected zone, and this area is as normal, which is good. What we see here is hardness values, and the hardness values in the weld metal is really low, and this is approximately the same as the yield strength. So the yield strength outside is close to 100. In the weld metal, it is less than 50. Outside in the heat affected zone, it is also around 50 and upwards. So you have actually lost all the performance of the weld. And this is due to this effect. This means that if you put any strain on these components or deformation, it will localize in the weld and it would crack immediately. So how do we do to avoid this? We don't want to have double as much material as you would like to have. So how can we avoid this softening in the what we call heat affected zone? We can very easily put the whole thing again in a furnace and reheat the whole component. Then you see that the material will have the same strength in all the weld. Okay, problem solved. But it might be a little bit impractical if the structure is large, like as an aluminum bridge or a vessel like this one or a car battery housing. So how do we do it in the MARBEL project? We use what we call intelligent design, where we compensate the heat affected zone by extra material when it is needed, but not more. So we designed this component here, which is the bottom floor profile, which is hollow. And this is just, you see, it's a prototype, so it's squared edges, but it is actually rounded. So if you do this with the right heat treatment and the right welding process, we localize this weak area, the blue one, only outside. So this profile here is as strong as the softer ones, the more narrow ones. And this creates an even balanced strength of the whole profile. So this is the good thing. But we have other challenges with aluminium welding. Aluminium is more susceptible to pores, and we have challenges with lack of fusion in most of the cases, where we try to apply as little heat as possible. So here we do a lot of experiments, try different welding procedures, and also try different shielding gases. The shielding gas creates different welding processes, and it narrows the arc and it creates a deeper penetration depending on what shielding gas we have. So we have chosen and tested different ones and found that argon-helium mixture with a little bit of hydrogen, Vargon for instance, is excellent for deep penetration and low porosities. So then we have a full penetration, low heat, and no pores. Okay, that's good. And then we do a study of the welding process. And this we do with a high-speed camera, which is especially equipped with illumination laser to study the arc welding in process. So we can then study how the welding process proceeds. And then, of course, the welds are, in this case, really good. The third problem, which is rather important as well, is distortions during welding. Aluminium distorts much more than steel because of the thermal expansion and also thermal dissipation. So here we design a lip and groove which connects each other in the assembly, which make the assembly easy and prevent deformation to a large extent. But however, we also have to develop welding sequences that reduces the deformation by reducing the heat input into the aluminium. And
Don't be afraid. That was only to wake up everyone.
yeah, I hope you woke up now. So we implemented this also with a robotic welding so that we can create almost perfect welds directly from the robot with no need for a further machining and very, very small. Sorry about the music, it was not my choice.
That was just to motivate the robot.
That was the first weld. I would weld on both sides in order to balance the stresses and not having deformations and no residual stresses in the component that can be detrimental for the performance. There you see that the welder robot does different welding differently. Not welding, one welding. That was our small prototype, which we have then produced in our. Thank you.
Thank you, Magnus. And again on time. Thanks a lot.
Okay, we take the questions to later.
Yes, yes. There are slowly from the audience online, there are already questions appearing. So we're going to answer them after the next session. So thanks, Magnus. The next one in the team is Antonio. So he is actually chief engineer with Agratis Innovation Division and responsible for co-design and activities on special projects developed with customers. So, and we will hear something opposite. Now we have talked about welded components. Now we do the opposite, unwelded.
Just fast. Okay. Thank you, Christian, again. So first, I would like you to show you who is Agrati. Agrati is a global manufacturer of fasteners, especially for automotive market. Okay, sorry. Yeah, you. For automotive market, I would say more than 90% of our business is focused on that field. And I would like you to focus on this number, 40 million pieces per day, which is a huge number of fasteners. That means that as our core business is our core process and it's transformation of steel from wire, that means that we manage every year something like 160,000 tons of carbon steel. That means that, you know, carbon steel is can get rust or oxidated very, very quickly. And of course, we are obliged as in the automotive industry, we have to protect it now by coatings. And this is why we are expert in that field. So please keep it in mind that later we'll show you why it is important for a MARBEL product. So, of course, we are a global worldwide company and different sites, 7 in Europe, 4 in US, and 1 in China. And so this DNA is very connected with steel and iron, but anyway, we are also so happy to work in innovation environment, and this is why we are here, because in this this part of the company, this division of where I take part, we developed the project together with the other friends. But let's go into the contents. Well, more or less 7 years ago, we started a project with a customer that asked us to solve a problem. They need to study a solution for connecting cells with high performance cells similar to capacitors. And they ask just for our competencies in coatings. They ask us to find the best way to connect the busbars and connect the cells in the module they would like to design. And that's why we develop our experience in this field. If you see these main guidelines, the last 4 are very connected with the ones of MARBEL project, and that's why we gave our contribution. While making research, of course, we soon learned that ECR, electric contact resistance, is the main factor in designing a solution for connecting cells. And different variables are important, you see there. And also so bring on this study, we also develop a setup test, and we developed some tooling set for making a study on materials, you can see there, and other variables connected with the importance of lowering at the maximum level the electric contact resistance. I can show you here a couple of diagrams, very interesting because they put in relation contact pressure with the different types of coatings. And you can see also there that nickel is a good compromise between cost and effectiveness. Of course, we worked on different solutions, and our final purpose was to make a proposal to that customer, which was a Japanese one. So it was a manufacturer of this type of cells, very special, very performance. And in the end, we make this proposal. This proposal, which work in some best parts of the matters related to the importance of gave a good electric contact resistant performance. Also, I would like you to show just this part, so wedge clamps and also conical spring washer, because we identified at that time the importance to have an elastic, to make some parts working in elastic domain in order to bear and to absorb vibration, and also we go into relaxation of materials. So in the end, we use all this information that we have performed during our studies, and also we use all this information into MARBEL project. Of course, in the end, you have to deal also that on some other constraints that are mainly related to geometry of the system, to the layout, the structure of the module to the position of cells, and everything is important to design and propose a good solution. In the case of MARBEL, of course, we have used prismatic cells that has some features instead of the other ones. But okay, so let's see how it has gone for MARBEL. Firstly, we have to face, just like some other companies of the consortium, the fact that we had to switch from one type of cell to another one. That in the case of busbar was very demanding, as the configuration passed from 6S1PE, so 6 cells in series, to 12 cells. That means 6 parallel. And you see that the contact point get from 2 to 4, and that was a complication for sure. And this challenge has been the most stressful one, I have to say, because in the beginning we faced immediately an issue due to the material that in the beginning, of course, thanks for the guidelines, we have to we would like to have to be 100% compliant with the guideline, so using aluminum everywhere and also in the busbar, but we have suddenly had to give up because of the fact that technology manufacture aluminum busbar for this purpose was not ready for the market, and it was a complication, and again we agreed with the okay, sorry. I was saying that this has been an issue, of course, because the technology for aluminum busbar in terms of flexibility, that was one of the main guidelines for our willing to design, was not possible to bring ahead that solution at that time. So we agreed with the project management of the project to switch to an hybrid solution. I say hybrid because of the main component of the busbar especially for cell-to-cell connection and module-to-module has been copper, but we have used the aluminum in 2 other parts, and you will see later. Another issue with after that, when the copper has been taken into consideration, so the first aim for the design was the flexibility. So we would like to use something like cable or a braid to maintain a high level of flexibility. And we had also issue with the compactation of the small portion needed to make the connection onto the cells. Until we finally found a good solution with this one that is made by copper foils, 0.1 millimeters, with nickel on top and bottom. Nickel on top and bottom for, of course, contact resistance on the contact part of the components. Of course, we calculated, we validated, and so on. And from this point, has been like a downhill, I would say. The third challenge, but it was a nice job, this one, has been the fact to design the extension to weld it on the prismatic cell. As you know, prismatic cells, if are not prepared for connection, it's really impossible to make drills, threaded drills, I mean, or other system, and also in that case we had to weld the extensions onto the tabs, and the extension design was really interesting for different reasons, and especially because we had optimized the path for make the welds, and we optimize also the design, thanks to also Tony, that we have collaborated to design this part which works like a radiator on the system, no, to exhaust the hot. And also the last part interesting is this one that works like a locking point for the screw during the assembly. So just a small advantage for the assembly of the bus bar onto the extension. You can see here also, so the behavior of the connection and the cooling channel that work on top the extension, like so which extract the hot. We have to take care also about the welding of the extension onto the tab. So you can think of 3,500 weldings, more or less. That's why we have designed this tooling set in order to make also an optimization from the welding point of view, because it's been so expensive, and also in terms of time. So need to be optimized also because using the technology of laser welding was very interesting to prepare a setup where the cells and the extension were always in the same position because of the focus of the laser inside the machine. And in the end, okay, this is the final result. You can see here some of the parts. Of course, in the end, we designed 5 types of different flexible bus bar to connect not only the cells inside the module, but also module by modules and all different configuration. And hybrid also because in the last mile, so between module, so the poles and the junction box has been done with aluminum bus bar, rigid one, but together with the flexible one coming out from the poles, so we have this hybrid and flexible final solution. Okay, thank you.
Thank you, Antonio. And in time again. And we even have a lot of time for the question and answer session now. So Violetta, Magnus, Tony, Silvia, Elias. If you see me watching my cell phone, you know, it's not because I'm waiting for some messages or something. I always get the instructions from the top management of the event today. Marina is doing a great job, so thank you for that. So we got a lot of questions already online, but before we answer those, I would say there are probably some questions in the audience as well. And I would love to start with you because, I mean, I've been talking enough for this session, I guess. So it's now up on you. There are probably a lot of questions to our speakers. And I'm coming to this side.
I have a question for Antonio. You know that we have different technologies of the batteries, so NMC, LFPs with different energy density. Do you also expect adaptation of the bus bar and the different link between the bus bar, depending on the energy that we have inside? And second question is maybe for everybody. So because we have different technologies, and so we have different expectation in terms of temperature and lifetime. So in terms of assessment and methodologies and test, so do you expect some variation of the material, variation of the design, depending on the different performances of the cell?
Thank you, Nello. So first of all, I forgot to tell you before that I have a call yesterday with our partner in this. So in manufacturing bus bar, of course, you know, Agrate is another kind of manufacturer. And this partner confirmed me that now this technology of foils, 0.1, 0.2 millimeters, is ready also for aluminum. So this is very good, a good information also for Alberto, who is interested, and Eduard for maybe prosecution of the project. Nello, to answer to you, yes, I would say that energy is not the first parameter from this point of view, or at least in my experience. That means that maybe also because we have faced until now only application of, let me say, high performance rate. And so we were more focused on optimizing the electric contact resistance, optimizing the contact area in order to avoid hotspots. That is probably the first problem for thermal runaway and other issues. Anyway, the delivery of energy could be an interesting parameter to make a second step of develop of connection in order to optimize them. Maybe why not reducing the cross section and reducing weight, which is only beneficial. Thanks to you.
So more questions. There.
Yes, a question regarding the joining between the aluminum profile. It's clear that welding doesn't preserve the microstructure of the materials. Have you evaluated the possibility to use solid state welding like friction stir welding as a joining technique?
Yeah, yes, of course. We have both considered solid state welding, either friction stir or the HIB technology, which is another kind of solid state welding, in addition to laser welding that creates less heat in the same amount of welds. But in this case, we had access to MIG or arc welding as a production technology from us, and therefore we choose that solution in this case. And it's also a little bit more industrialized. But in the future, yes, we could have used solid state joining. That's for sure. Just one question. In some of the corners of the welds, it would have made a little bit tricky to have the same design because you have to have the pressures from the both sides. But in the floor panel, yes, that would have been possible.
Maybe I can give a small addition to that. For industrialization, we are also working for the friction stirring welding. And it will be possible for the maybe future researchers to implement the friction stirring welding to the battery housing profiles. Yeah. And also we would be fixing the industrialization problem then.
As we talk about welding already, there's one question from the online audience. It was, how does sophisticated and much welding balance against larger dies and extrusion commercially and LCA-wise? I would say that's a question as well for the three of you. So who wants to answer? Just had on the microphone. Yes. The question was, it was meant to Magnus, but I think it's a question also for Violetta and for Elias. How does sophisticated and much welding balance against larger dies and extrusion commercially and LCA-wise?
Well, that's first of all, that's a good question and maybe Ashas can help us with the extrusion dies and that part. We have chosen a welding wire material that is compatible with the base material. So from a recycling point of view, this solution is not giving any challenges. But when it comes to LCA, I think you have to.
Don't struggle.
I only know that if you mix materials, then it's very difficult to recycle at the end of life. So if you're using the same, you have more possibilities, as Magnus was saying. Then,
Yes.
So
use
like,
the microphone.
yeah,
Or the online audience won't hear it.
actually, like getting larger panels can implement or can be solve this problem to prevent the welding, and also like other, but still you need to then investigate the welding behavior or the tolerances, because that's such a big profiles. If you produce that kind of big panels, then you're gonna have to make the welding at the end of the day, and with big such panels, and it becomes larger, harder to get rid of the distortions of the panels. Yes, I don't know, maybe LCA point of view or welding point of view, it would be nice, but then it comes with another different problems. So.
And just a small addition, the modularity required us to have panels that could be added 5, 4, 6, 7, 8 different amount of panels in between or in different lengths. So the modularity was kind of one of the prerequisites.
More questions in the audience?
Hello, so my name is Stefano Montani from ScienceCo. My question is related to the modularity and the busbar. So I understand the modularity concept where you try to replicate the same components, but what about the busbar? I guess that 400 volt and 800 volt have different requirements in terms of flame retardancy and electrical insulation. So how can you keep the modularity concept when the requirement changes?
Oh, okay, we use the same because the idea of this battery is to have two half batteries. Okay, then we have in the 800 volts, we have one 400 volts battery and another 400 volts battery. Okay, and then the junction box, it's the electronic part that translate this battery depending on the demanding in a one battery of 800 volts or 400 volts. Then we use the same bus bars, okay, from the module to module and also to cell for both batteries. Okay, and the only bus bars that change are the bus bars that comes from these modules to the junction box. Okay, not only for the necessity, also for the dimensions, because it's not the same junction box, and as we use the same box, we have to change the size of the bus bars. Okay, but the idea is to have the 800 volts formed by two 400 volts batteries. Okay.
Okay, thank you.
Fleur de Blechuger, UL Solution. I just want to know if you consider to use a thermoplastic or composite material for housing.
Yes, the idea in this project was to use aluminum from the beginning. Okay, but the idea is to try to reduce the weight, but also to increase the recyclability. And it's for that you use aluminum in not only in the housing of the battery pack, also in the housing of the modules.
Any more questions over here? We got lots of them already online. So maybe, Antonio, some questions. Can the mechanical joint proposed by Arcati be automated, or shall it be always done by hand? That's a good question. If it goes to serial production, I guess the answer
is no, of course. One of the guidelines is also to design something very easily to be automatically assembled or disassembled. Of course, in this case, we were inside the prototype phase, so no need to develop any special feature from this point of view.
A critical question that is probably not that easy to answer. Also, if you got the microphone once in your hand, which is the added weight per cell added by the mechanical joint of Arcati? That's a good question. If it's not welded, of course, there is added material, but
well, I would say from the overall point of view, if you think that the importance is the cross section, I would say that the added, it's only located into the fasteners, okay, that you provide more. But on the, so
probably a few %,
Thanks.
to be honest.
Yeah, some more questions. The defined functional unit for the LCA. A question to Violetta.
That's a very specific one.
Yeah.
This is coming from an LCA expert for sure. For the rest of
Yes,
non-LCA, for the non-LCA experts, the functional unit is the basis for the calculation of the life cycle assessment, which serves the purpose is to maintain a standard that is based on the function that the product that you're evaluating is going to perform. So for example, a bottle of water would be, the functional unit can be the transportation, the storage and transportation of an amount of water. So if you compare this bottle that is one single use against one that has many uses, then the transportation of this 200 milliliters of water is going to have less impact when you reuse the bottle than when you throw it away, right? So in the case of the battery pack for MARBEL, we define two different functional units. I don't have them on the screen, but for some reason I was expecting it. But we define two different functional units because there are many studies that study electric vehicles performance in terms of kilometers covered by the car. But then there's other studies that cover this assessment by kilowatt hour that the battery can give you during the lifetime. So we use first the kilometer until the use stage of the battery, and then we perform the same study, but then including the second life and the end of life of the battery with kilowatt hour, because maybe the second life is not really required that it is also covering a distance. It could be a stationary battery at the end. So in this case, the kilometer makes no sense. So we use the both functional units.
One more question because it's related to the LCA topic as well. Someone is asking for the reference we compare the LCA with.
Okay.
It's the same person.
Yeah, probably, most likely. This was we did a literature review on this, and we found many papers on it. So we did an average on the available papers on this topic, and then we compared it with the grid model that is available online. I'm sure, well, she can find it online. And mainly, I would say the main basis of the assessment started with a paper from Accardo et al. From Polito University, Politecnico de Torino. Yeah.
All right, thank you.
Yeah.
One question to Sylvia. It's one that was questioned here in the audience as well, and I got the same question. You were talking about aluminum alloys and extrudability. Extrudability sounds something that I can't measure. How do you measure extrudability?
Well, yeah, as I told you before, we need to know what happened when we increase the scrap and we have impurities. And we equipate our tooling with 3 different sensors to measure the pressure, temperature, and the distance to evaluate this property.
All right. So this way you see the, Elias, yeah.
And also Shepard has made a list about it, about the extrudability of the alloys. Maybe flow stress, but is not certain. Flow stress would affect the extrudability of the alloy, but we know that increasing excess silicon in the alloy and increasing iron content. And if you increase the scrap, then it means you cannot get rid of the iron content. So it forms intermetallics and it increases the flow stress of the material. That's why it also affects the extrudability of the alloys. So
perfect, thank you. Some more questions in the audience?
Thank you very much. So, Maide Rusabiaga from Ikerland Technology Center in the Basque Country. Thank you very much for very interesting presentations. My question is around the screwed joints you have been working on, especially when you're joining the similar materials I was wondering if you also included some durability tests of the joints you were making by a screw to see if the initial low internal resistance value was maintained along the lifetime, taking into account the conditions that the battery pack will have to suffer along its life. Thank you.
Thank you to you. Okay, for sure, in this case, not yet, because the tests, also vibration tests, are foreseen in the next steps. But yes, usually what we take into account during the design phase is absolutely trying to insert an elastic element that is for absorbing vibrations and for the overall assessment during the lifespan of the connection. Also, we are very, I would say, expert from this point of view, as the tightening strategy for us, it's one thing that usually we do for customers for any kind of connection, of threaded connection. And that's why it is very important to know coatings and to know the coefficient of friction. Through this information, we are able to design a precise tightening strategy, able to guarantee over the lifespan the results. And also coatings from corrosion point of view, so both the things together.
Thank you. I'm sure there are more questions, but for the online people, just write them in the chat. We will answer them later on. There are some more we can't all answer today. I would say there is only me standing between you and the coffee break. So I don't want to be in the way. So we have the coffee break right over here. And thank the speakers again. And to answer the rest of the questions with a coffee in your hand.